Hello and welcome to HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 14, we'll talk about parametric and non-parametric tests. So let's get started. Before we get into the details of parametric versus non-parametric tests, we have to talk about measurement scales. There's really four different types of measurement scales. You can see them over in the chart to the right. We normally talk about them in terms of the level of sophistication. I like to refer to them in the opposite order. Instead of ratio being the first one mentioned, because it's the most sophisticated, I normally mention it at the last. And that makes a nice mnemonic that we can remember called noir. If you know French, that's the French word for black. And noir is a good way to remember both the order as well as a hint as to which particular measurement scale we have. So nominal, ordinal, interval, and ratio. So here they're in the right order in terms of going from least sophisticated to most sophisticated. There's a lot of things that we can do with some of these, the more sophisticated ones, that we can't do with the more crude or basic ones. So let's start with the most crude one first, which is nominal. It's also called categorical. So this is where we arbitrarily assign a code to an attribute or a category. So for example, license plate numbers, state codes, postal codes, military rank, gender, male, female. The problem is we can't do a whole lot of mathematical manipulations. About the only thing we can do is categorize them and count them. So think about things like gender or state of residence. We can count them, but there's no implication of order between these. So again, we just use them with frequencies. So there's really very little we can do with these particular types of measurement. So when we have a categorical, we can do a ratio scale measurement. So that's basically just a count. So we can compare count values. There's some statistical measures that we can do with nominal and categorical data. Now, the second one in terms of sophistication is ordinal. So this implies order, and this gives a ranking, which can be any kind of characteristic. So for example, if you have 3 different types of phones, and you want to put them in some kind of ranked order, or 3 GPS systems. So the main limitation of ordinal data is that the interval is not intrinsically equal between different points on the scale. So how much more important if you have a ranked choice is the first choice compared to the second? So it's a little bit more sophisticated than nominal because we can make comparisons in terms of order. But it's still not possible to define a mean. I mean, how would you take a mean of a ranked set of values? So the third measurement scale is called interval. And interval has equal distances between adjacent values. So unlike ordinal, where we don't know if somebody's first choice and second choice have the same interval as between their second choice and their third choice, with interval, we can be guaranteed that the gaps are the same. However, there's no absolute zero on an interval scale. So unlike ordinal data, it is meaningful to compute the mean of interval data. So finally, we can get to something where the mean actually matters. So the mean midday temperature during the month of July, we can take a look and calculate the mean temperature, right? So ratios are not meaningful. We can't say the temperature in July is double the temperature in January because temperature, at least in Celsius and Fahrenheit, does not have an absolute zero. So we cannot say that 20 degrees is twice as warm as 10 degrees. The fourth one, and the most sophisticated, is ratio. Now, ratio has an absolute zero. So if we were taking temperature and we went to Kelvin, there's no negative value for Kelvin, so there is an absolute zero. whereas with Celsius and Fahrenheit, we can't say that. Height, that has an absolute zero because there's no negative heights. And weight. Weights do not have a negative value in terms of humans or different objects that we want to weigh. So we can support a lot of different calculations that we couldn't with the other three. And that's why this is the most sophisticated. So we can do different things like add, subtract, multiply, and divide. So we can take a ratio and we can say that person is twice as heavy as the other person, or that person is twice as tall as another person. So we can calculate means, we can calculate standard deviations, and we can calculate variances. This gives us a lot of latitude in terms of what we can do with this data. So let me give you a couple of additional examples of each. So with nominal, it's used in research surveys and questionnaires where only the labels hold significance. Where do you live? Which brand of smartphone do you prefer? So you can see in this example, we can't assign any kind of order to where they live. We can't assign an interval because it doesn't make sense that the distance between somebody who chooses city versus town is equal to somebody who chooses suburbs versus city. It just doesn't make sense. Also, smartphones, Apple and Samsung versus Samsung and Motorola, there's no ordinal value between the two. It's just a simple choice. And second of all, we can't do a ratio if we assign the 1, 2, and 3 to these brands because it's really arbitrary. So there's two ways in which we can collect the data. Typically by using an open-ended question and then code it to a respected number of a label. So for example, what motivates you to do this task, for example? And then the person answers, and then the researcher has a list of perhaps 10 different categories and puts that answer, even though it's open-ended, into one of those categories. The other is to collect the nominal data, including a multiple choice. So I often get when I delete software, they say, what reason did you choose to delete the software? And they give me like a choice of 5 or 6. In both cases, we can use percentages or we can use mode most often. So it is possible for a single question to have more than one mode, just like you can have 2 favorites or 2 items on a list that you like least. Here's some additional examples for ordinal. So you have to remember order, because of the name, order is important. So they're usually used to depict non-mathematical ideas such as frequency or satisfaction or happiness or degree of pain. So the implementation of this scale is just like it says. There's some order to it, but we can't say that the order between adjacent points is equal. The gaps are not equal. So for example, here are some examples of items that we can use an ordinal scale for. And they can be used for market research to gather feedback about how satisfied they are, their perceptions with different types of upgrades. We can certainly do this with many aspects of HCI. If we have a semantic differential scale question such as, how satisfied are you with our services? You can see that order is always going to be the same, right? So it's never going to be the case where satisfied is lower than very unsatisfied. So the order is preserved between the questions. What we don't know is how big is the gap between very unsatisfied and unsatisfied compared to the gap between unsatisfied and neutral. So this is where we have additional abilities or sophistication with the ordinal scale compared to the nominal scale. And analyzing the data really helps us do certain things that we can't do with a nominal. Now let's talk about some additional examples with interval. So remember, interval is a numeric scale where the order is known as well as the difference between the variables. Remember, what sets the interval apart from ordinal is the fact that the units are equivalent, or the gaps between the different variables. So interval indicates the distance between two entities, which is really what we're doing with the interval scale. It has all the properties of the nominal as well as the ordinal scale, as well as the ability to calculate the difference using subtraction or addition between variables. So the interval allows us to do this addition and subtraction. For example, Celsius and Fahrenheit. So we can say that the difference between 80 degrees and 50 degrees, first of all, 80 is always higher, and the difference at 30 degrees is the same as it is between 70 and 40. So that allows us to see that the interval, in other words, we have 2 points, we can do addition and subtraction between them. But one thing we can't do is we can't do multiplication and division. Remember, in Celsius and Fahrenheit, 0 is arbitrary because you could have negative values, so there's no absolute 0. So we use interval scale when we have the difference between the variables is important, which we can't do with the less sophisticated scales of nominal and ordinal. So this allows us to look at the difference, and we can calculate things like mean and median in addition to mode. But apart from temperature, there's also several examples. For example, calendar years and time also fall under the measurement of interval. We can use Likert as an interval when we have, say, for example, 10 different values, and we can say, how satisfied are you? 0 meaning not satisfied, and 10 meaning extremely satisfied. The idea is the difference between two different values between 0 and 1 is the same as the distance between 9 and 10. But we'll talk a little bit about that at the end of this lecture. So here's a couple of questions that could fall under interval. What is your family income? What is the temperature in your city? The last one, in additional examples, is ratio. So this one we can calculate the central tendency, which we can't do with the others. So we can do mean, median, mode, and things like geometric mean. We can do variation and harmonic mean. So this allows us to look at all the other three, nominal, ordinal, and interval, but we can also do things like calculate the difference between values and also do multiplication and division. Because we have a true 0, we don't have negative values. And so we can find an absolute 0, meaning there's no values less than that. So this allows us to compare those. So mean, median, and mode can be calculated using the ratio scale. Here's some questions that we can use the ratio scale category to answer. What is your daughter's current height? And then we give a couple of choices. And what is your weight in kg? And you can see here, we have a couple of different options here. But we can take the mean or the midpoint of each of these. We can get some additional statistics based on those means of each of the 4 values and compare them. So in HCI, let's take a look at some ways in which we can use these measurement scales. So again, here are some of the ways in which we can do it. So we can count the number of observations, we can categorize things, we can count things with nominal, we can get ordinal data, having people rank things. With interval, we can use a Likert scale, and with ratio, we can do things like task completion time, number of button clicks, the distance or the velocity. We can use age because it's got an absolute 0, or years of experience, right? Because we don't have a negative for those values. So here might be something which we can do. So let's talk a little bit about parametric tests. So far, we've talked about a few different tests. We started with t-tests. We talked about ANOVA. We talked about correlation. Then we talked about regression. So really, these are parametric tests. And these require certain assumptions to be made about the data. First of all, we're assuming a normal distribution. We also have scaled intervals. So we know that, for example, test taking. If somebody scores a 70, that's going to be 5 points greater than a 65. If somebody scores a 90, it's going to be 5 points greater than an 85. the intervals are standardized. We're also assuming an equal variance in the measurements that we're taking. So with a normal distribution, we assume that we have this bell curve, and you can see the variance is perhaps each bar, and you can see that the most bars are right towards the mean. And as you go out on each side, the dissipation of those values is going down at the same degree. So with scaled intervals, we have any two adjacent points should be equal. And I mentioned that with the test scores. So age, so the distance between somebody who's 2 versus somebody who's 1 is equal, right? But could we say that somebody who's 10 is twice as old as somebody who's 5? Could we? We can, because there's an absolute 0. So 1 and 2, 2 and 3, 80 and 81 all have the same gap, and that's 1 year. So that 1 year is true regardless of what 2 points we pick, as long as they're adjacent. So we're assuming equal variance. So we want to make sure that the variance, remember the x bar is the mean and the x is each data point. We're taking the square of that difference divided by 1 less than the sample size is going to be the square of the standard deviation, or the variance. So the higher the variance, the more distributed the data set is. So if you think about that bell curve, the bell is going to be more flat and not go as high in the middle, the more the variance is. With non-parametric tests, we can do certain things when those assumptions are not met. Sometimes we have categorical values, such as race or gender. So we might have counts of those. Ordinal values, such as a ranking scale, where different items are compared directly with each other. So do you prefer Samsung or Apple? Do you prefer pointing devices or a trackball? So in those cases, intervals are not equally spaced, because the difference between Motorola and Apple is not the same as the gap between Apple and Samsung. It just doesn't make sense. Here's an example with a Likert scale. So here we want to make the assumption that the distance between each of those points is equal. But we could possibly have unequal data points, right? Order is preserved, right? So we always know that 3 is greater than 2, neutral is greater than disagree, but how much more is the difference between neutral and disagree and highly disagree? Also, when we have yes or no questions, we could have the same issue, and also with ranking, because my first choice might be really, really my favorite choice. And the second one I'm lukewarm about, and the third one I'm almost the same as the second one. So we can't preserve that interval. We can only preserve order. What non-parametric tests do is, when we can't meet those assumptions we talked about, we need to consider non-parametric tests. We make no assumptions about the probability distribution. So they're applicable to a wider range of data than parametric tests. However, there's a lot of different tests, and keeping track of them is what we'll talk about over the next few lectures. The downside is you lose information. When we have a normal distribution, we can make certain assumptions about how the data is distributed. With non-parametric tests, that's lost. So, for example, ordinal data. So while parametric tests operate on interval or ratio data, remember, those are the most sophisticated, non-parametric tests ignore any property of the scale except the order in which they occur. Remember when we were talking about correlation, and we used Pearson's R, but there were some other options like Kendall's tau? Those only worked with ordinal data, whereas Pearson's R allows us to work with interval data. So it's a more powerful test. And then in general, when we have a more powerful test, we're going to give a more concrete and confident message that our test is indeed backing or refuting our null hypothesis. So it is possible if we had interval and ratio data to do a non-parametric test, but it's kind of a waste. It's like having a Ferrari and then using it to go through a neighborhood where the top speed limit is 25 miles per hour. It just doesn't make sense to do that given the fact that we've got all these additional tools available to us. Let's look at an example of a non-parametric test. Students' marks on an exam, or their scores, were 49, 81, and 82. So we have three different values, assuming they're on the same scale of 0 to 100. The interval between each mark or each point on that exam is the same. So the gap between 49 and 50 is the same as the gap between 81 and 82. There's an absolute zero, right? People can't get a negative score on the exam, let's just assume. So this would be a ratio scale. It makes sense to say if somebody got an 82 versus somebody getting a 41, we can say that the person who got an 82, assuming it's a 100-point scale, got twice as good of a score as the person who scored 41. If we transform it into 1, 2, 3, say 3 being the 82, 2 being the 81, and 1 being the 49, it would be an ordinal scale. Can you see how a lot of information is lost by just preserving the order only? You can see that the distance between 3 and 2 and the distance between 2 and 1 is equal, but it doesn't really reflect on how those scores on the exam. So there's a trade-off. There's no parametric assumption. So we're not assuming it's got the variance as equal, it's a normal distribution, and so on. But we sacrifice power of a bunch of information that can give us more confidence about rejecting a false null. In exchange for less strict assumptions about the data, we lose that power. So when do we want to use these non-parametric tests? When we have ordinal and sometimes interval data, such as rankings or perhaps Likert values, when we obtain data through questionnaires, through preference rankings or ratings, doing an assessment on a certain scale, like 1 to 10, rather than using direct measurement of human responses, we can obtain subjective information from participants or use some heuristics or some kind of non-empirical or semi-empirical methods. Now, let's talk a little bit about some controversy. Here we can see a ordinal scale between strongly disagree all the way to strongly agree. And this is what we think as interval data. Remember what interval data reflects. It reflects the fact that the intervals between each of these 5 points for each question is the same. So if somebody gives a numeric code, such as 5 or 2, depending on the question, we can say that it's symmetric about a neutral central value, right? So if I look at the scale, I would assume that most people are going to rate it neutral, and then those are going to be less likely to rate it mildly disagree or mildly agree. And then the outliers, or the really far ones from the center, are strongly disagree and strongly agree. So the gradations between each of those 5 should be roughly equal. But there's some disagreement on whether those are truly equal gradations because of how we think about the 5 different points. Do respondents perceive the difference between strongly disagree and mildly disagree as the same as between mildly disagree and neutral? What happens if we have 10 points? You can see as we widen out the Likert scale, the gradation between them gets harder and harder to distinguish. There's evidence that the respondents perceive items at the extremes as further apart than items in the center. Their view is kind of like that normal distribution, and they look at things like the 1 and the 5 on that example as outliers almost. So one remedy is to simply instruct respondents to interpret the items as equally spaced. So we have to tell them this so that they realize that the interval is actually a true interval. So keep in mind that instructions do not guarantee that they will be followed. So let me show you an example from Amazon of, I'm just going to take an arbitrary thing here, which is a mouse. And you can see here that 59,000 people have chosen this mouse. So looking at that mouse in more detail, we can see that there's 77% 5-star reviews and 13% 4-star, etc. So we can see this is not a normal distribution. Second of all, it's kind of inferred that the distance between a 5-star and a 4-star and the 4-star and the 3-star is not interval. If we had a normal distribution, for example, we see most people would think it's a 3-star, with fewer people thinking it's a 4 and 2, and then even fewer thinking it's a 5 and 1. However, with customer reviews, typically the idea or the mindset is that if they don't give it a 5-star, then there's something wrong with the product. And you can see here by the features below, quality of material 4.5, portability, durability, etc. This makes it very challenging for us to do any kind of interval-based statistics on these customer reviews. And you're going to find this true with a lot of different types of review-based measurements. So thank you very much, and I hope this has been informative. I'll see you next time. We'll talk more about non-parametric tests. Thank you.